So good morning everyone. So this is the August 14th and we are starting with HVSR, or that is the site characterization technique. Before we move into that part of this engineering seismology course, let's have a recap of what we have learnt yesterday. We learnt about dispersion, and dispersion is the velocity varying with frequency and the wavelength, and also you can say it is varying with period. So it is similar to the phenomena of light, where the different frequencies of the white light gets distributed into its different component after falling onto the prism. So this is the expression for dispersion. So velocity is varying with respect to lambda. You can replace it either with frequency or maybe with period, and the phase velocities are a function of omega and k. So omega being the angular frequency, k being the wave number. And we also saw the dispersion happening into the tsunami. And for tsunami, if there are long period waves, the dispersion phenomena won't occur. And we also said that the waves, for example SH wave, when they reach to the surface, they get trapped over there, and the reflection, multiple reflection phenomena occurs over there, since the material is anisotropic and heterogeneity is there. So the waves will be varying slightly with respect to the frequencies and the wave number, and they will superimpose with each other and will result into the phenomena of dispersion. So we derived this expression yesterday for the displacement of the superimposed waves, where one wave was the envelope wave and another one was the carrier wave. And for the carrier wave, the velocity was omega by k, and for the envelope wave it was delta omega by delta k. And this was the envelope waves, and inside which you have the carrier waves like this, and the carrier waves generally travels faster than the envelope wave. Thereafter we saw the carrier waves are nothing but, we call it as the phase velocities, or the wave velocity of the carrier wave is equal to the phase velocity, and we also call the envelope velocity as the group velocity. Thereafter, since delta omega and the delta k is almost equal to 0, so we can write for the group velocities d omega by dk. Thereafter we derived the relationship of group velocities with respect to wave number and the phase velocities. So this was the relation we saw, u is equal to k dc by dk plus c. Okay, so in the case the wave is non-dispersive, so this dc by dk, k is the function of lambda, will become 0. So envelope velocity or the group velocity will be equal to the phase velocity. Thereafter we derived the relationship of the group velocity and the phase velocities with respect to lambda. So the expression was something like this. On the broader scale, if you just want to see the relationship between phase velocity and the group velocities with respect to lambda, then the relation may turn up into like this, right? And then the same thing, since the velocities are varying with depth, as you go deeper, the higher velocities you will reach to. So higher wavelength will penetrate deeper, so dc by d lambda will be always greater than 0. So this also relation proves that the u is going to be less than c. And this is the typical dispersion curve with respect to period, and we computed it for a synthetic model where we consider a single layer Earth model over a half space. For the half space, the velocity, shear wave velocity beta 2 is given and the density rho 2 is given, and here the shear wave velocity is beta 1 and this is rho 1. And for this model, we generated the group wave velocities for love wave and for the phase velocities, and it turned up into like this. So you can see the phase velocity dispersion curve is above the group velocity dispersion curve. Now we saw the dispersion phenomena in the case of real Earth scenario on the data recorded at the station in New York for the Californian earthquake, and here we saw there is a wave pulse periods that is getting decreases with respect to the time. So that is basically naturally the phenomena of dispersion it indicates to us. Thereafter we learnt how to calculate the group velocities in the most simplest manner, but actually it is computed in a very sophisticated manner using the fast Fourier transform. And then we saw the example of this Mongolian earthquake recorded in Japan from a large distance, and then this is the unfiltered seismogram, and these are filtered at various periods. As you go deep, as you go from top to bottom, the period is increasing. So the higher period waves you can see are coming earlier. As you decrease the period, then the arrival times also decreases. So this is the phenomena we saw, and then we took this example of the mid-Atlantic rift, or mid-Atlantic ridge, that we call it Walvis Ridge, and there is an earthquake and there are two stations here. One station path is along the ridge and other is off the ridge. So thereafter, from the data, surface wave data, we computed the group velocity dispersion curves, and along off the ridge, the dispersion curves group velocities are higher than the on the ridge dispersion curve. And thereafter you can use some kind of modeling technique to invert the dispersion curve in order to get the shear wave velocities. So group velocities are being converted to the shear wave velocities in order to find out the bulk properties of the crust and the mantle. So you can see the shear wave velocities for the off ridge region are higher than the on ridge region. That may be due to the hot spot present over there. Then we also saw the codes for the Bob Herman that may be used to do this kind of modeling. Thereafter we took this example of Nishimura and Forsyth published in 1989 for the Pacific Basin for different 5 ages provinces, and you can see this is for the oldest crust and this is for the youngest crust, and thereafter when we modeled it, the oldest crust had the highest velocities. Now thereafter we discussed about the tsunamis, and tsunamis also displays the phenomena of dispersion similar to the Rayleigh wave and the Love wave, and for the longer period tsunami that is comparable to the depth of the ocean bottom floor, then the phenomena of tsunami dispersion will be absent for the longer period waves, and in that case the phase velocities will be simply equal to under root g into d, where g being the acceleration due to gravity and d is the ocean depth. And if you are talking about the shorter wavelength tsunamis, then the formula may look something like this, and you can see the phase velocities now are getting dependent upon the wavelength of the tsunami. Okay, so the phase velocities now are the function of wavelength or maybe frequency and the period. And in order to confirm this in the case of real Earth scenario, then there is a record of tsunami, and you can see the larger period waves are coming earlier than the shorter period waves here. And then if you look at in terms of the dispersion curves, then you may see the longer period waves are basically showing almost flat dispersion curves, indicating towards the group velocities and the phase velocities are same for the longer period tsunami waves. While if you look at the shorter period tsunami waves, then there is a difference in the values of group velocities and the phase velocities. Now, if we move further, now we are going to start with this topic of site characterization techniques. So, if you remember that there was a surface, then we had a bedrock, and in between there were the soil layers. Okay. So, using PSHA and DSHA techniques, you can possibly find out what are the motion occurring at this particular bedrock. So, this is your bedrock. So, now the task comes how this bedrock motion will reach to the surface. Okay. So, finally, for the engineering design purposes, you have to calculate these surface motions that are coming from the bedrock, and in between you have soil layers. So, for the soil layers, you need to find out some kind of transfer function using which you can convert the bedrock motion into the surface motion or the ground motion. Okay. So, you need to basically do some kind of laboratory test or maybe the field test in order to characterize this soil and find out its elastic properties, so that using those elastic properties you can find out how the bedrock motion is reaching to the surface. Okay. Now, if we look at the little bit of basics, then most of the earthquake damages occurs due to the ground amplifications, which for the same earthquake magnitude change with ground stiffness at relatively shallow depth. That means the stiffness of the soil is basically very essential in order to do the amplification. So, soil is, or the superficial soils are something that may amplify or de-amplify the bedrock motion. Okay, if soil are very loose, then the shear wave velocity or the stiffness of the soil will be less, and it will amplify the waves as it reaches to the surface. Now, as per the standards, the top 30 meter of the soil influences most, and the shear wave velocity for this top 30 meter layer is the best indicator of the stiffness. So, that is why most of the time we are mostly interested to find out what is the average velocity in the top 30 meter layers of the surface of the soil. So, that we basically represented by VS30, okay, and that VS30 is we are interested in to find out, in order to find out the site response at a particular area. Now, if we go further, this is the program which was established by United States Congress in 1977. The name was National Earthquake Hazard Reduction Program. So, if you look at this name, they say that the National Earthquake Hazard Reduction Program. There is some tricky part in it, because they are saying it hazard reduction, which is not possible. So, you can reduce the risk but not the hazard. So, this is established in 1977, adopts this criteria and classifies the site into several different categories based on the soil present over there. And after 1977, in 2000, there was another code was established, the International Building Codes. They also suggest or recommend this criteria should be followed. So, this is the criteria by NEHRP for the site classification. So, there the site classes are given. Here you have the shear wave velocity in feet per second, and you also have shear wave velocity in meter per second. Okay. If hard rock is present, having velocities greater than 1500 meter per second, then you will classify the site as A, site class A. If it is in between 760 to 1500 meter per second, then you will classify the site as B, that is the rock, and then you can classify it in between 360 to 760 as a very dense soil or soft rock. And if it is in between 180 meter per second to 360 meter per second, then you will classify it as a site class D, being the stiff soil, and less than 180 it is soft clay or soil, and thereafter you have the site class F. Now in order to estimate the shear wave velocity for the top layers or the superficial layers, so this means that these classifications are updated in 2023. Okay, so I will try to find those out and will post it into the group. Okay, now look at the Vs or the shear wave velocities can be calculated or measured using different kind of field setups. For example, you can do surface wave surveys, and also you can do like refraction survey, downhole survey, cross hole survey, and other laboratory measurements you can do. But the surface wave survey deals with relatively low signal to noise ratio, and a high signal to noise ratio is a most crucial factor in all types of wave based techniques to ensure a high accuracy in the results. So these are the typical setup is given, like there is this refraction survey, you have some active source and there are some receivers along an array. As soon as you excite the source, the waves will basically generated in the form of half spherical wave fronts, and as it reaches to the receiver, it will record the seismic section, and you can do processing in order to find out what are the layers present over there. Likewise, you can place your receiver in the borehole and measure and do your active survey from the ground, and whatever energy will reach to the borehole, using which you can find out what is there inside the top superficial layer of the earth. Likewise, cross hole survey, you can dig out 2-3 boreholes and you can drop the receiver in, and on the other borehole you can basically excite the source. That is your for your cross hole survey. So these are the some of the papers that we published from our lab for the site characterization purposes, and this is just for the information. So we conducted our study for Dhanbad city using equivalent linear analysis that were complemented by HVSR ratio. So we also conducted joint modeling and the uncertainty estimation for the site characterization of Dhanbad city using global optimization. We also used earthquake data to calculate the horizontal to vertical spectral ratios likewise. Now, before we move on to what is HVSR technique, let's have an understanding what is ambient noise. So ambient noise is a background noise that is widely spread, and it is present almost everywhere, and these are the causes of the ambient noise. So it can be generated by oceanic excitations, atmospheric activities such as the wind and storm, and also it can be generated by human activities. So ambient noise mostly consists of surface waves. These are low frequency waves mostly below 1 Hz that are also called as microsize, and it may be generated due to the natural causes, mainly due to the oceanic waves. So when we jump on to the understanding of HVSR curve, it is sometimes also known as HYV technique, HVSR technique, or maybe from the name of its discoverer, that is Nakamura. So Nakamura technique it is also known as. So horizontal to vertical spectral ratio technique, it's a very widespread tool, and you will find a lot of papers based on this, trying to estimate the shear wave velocities for the superficial layers. And this technique is used to study the ground motion amplifications and from the microtremor data or to the strong motion data. And HVSR technique is very popular, and because it is a very low cost tool and not a lot of manpower is required, and it can be applied both to the ambient noise and the weak motion recordings. Large amount of site characterization studies has been described in literature, and recently this technique has been used for many different purposes, such as the studies of sedimentary basins, faults, cavities, and finally to estimate the fundamental frequency of the buildings. So the technique was initially proposed by Noguchi and Egarshi in 1971, and it was widespread by Nakamura in 1989. It consists of estimating the ratio between the Fourier amplitude spectra of horizontal to the vertical component of the ambient noise vibrations recorded at one single station. So basically what you are doing in order to compute your HVSR curve, you are supposed to keep an instrument, seismometer, you can use short period seismometer, and then you can take it into the field, keep it at a place of investigation for around 40-50 minutes. So let's suppose this is the recording that you are having. So this is the top one is the vertical component, and the middle one is the north-south component, and the last one is the east-west component. So this is the entire maybe 50 minutes of recording that you have. Okay, now what you are required to do, you need to divide this entire continuous recording into number of stationary time windows. So stationary time windows means the signals mean variance and the frequencies in each windows are not changing much, it is quite stable. And if there is any spike due to maybe, for example, maybe due to the truck or maybe the electrical wire lines, then you will have to apply an algorithm, that is anti-triggering algorithm, that will remove any kind of short burst that is present in the signal, and or maybe it will remove the transient noise. So after you convert this recording into number of stationary windows, for each window you need to do the Fourier transform. So you are going to convert time domain signal into the frequency domain, and then in the frequency domain the calculations will be simpler. So now after you do that, for each window you will have to compute your fast Fourier transform. So this is for one window, that is vertical component, that is your north-south component, here you have east-west component, okay, in the Fourier transform. And thereafter you will take the average of both the horizontal components, you will take the mean of the horizontal component, okay, and then this is the mean and this is the vertical component, and thereafter you will divide the horizontal component mean by the vertical component in order to get your HVSR curve. Okay, so basically you are what you are doing, you are having 3 recordings. So like this is your continuous recording for 50 minutes for the vertical component, then you have north-south component, this is your north-south component, then you have the east-west component. Okay, this is your in time series, this is your time series, and then you are dividing it into the number of windows. Okay, you have divided the data, and for each window such as this one, you are going to do the fast Fourier transform for east-west component, north-south component, as well as the vertical component. Okay, for after you do the fast Fourier transform, maybe it may look something like this for the vertical component, it may look something like this for the north-south component, and it may look something like this for the east-west component. Okay, so here you have the amplitude for the vertical component, here you have the frequency, this is the amplitude of the north-south component, here again you have the frequency, this is your frequency, and this is the amplitude of east-west component. Okay, and thereafter you take the mean of the horizontal component, which may look maybe something like this. This is your mean of horizontal component, this is your mean, and here you have frequency, and then divide this entire spectrum with respect to the vertical component spectrum, and then you will get your horizontal to vertical spectral ratio. So that is why it is very simple technique and cost effective also, and it is not that labor intensive, because you are just carrying a seismometer, going into the field and putting it at one place and waiting for 50 minutes, and your data is recorded. Thereafter you bringing the data back to your laboratory and putting it into some software, for example Geopsy or maybe other software, Gorilla or whatever. So using that software you are going to do all these processing operations to calculate your horizontal to vertical spectral ratios. Okay, so basically once you compute your HVSR curve, maybe let's suppose your HVSR curve is looking something like this. Okay, you have your frequencies here, you have your HYV amplitude on the y-axis. So the largest frequency, the frequency associated with the largest amplitude is basically known as the fundamental frequency. Okay, this is your fundamental frequency, and it is generally associated with the contrast, the highest contrast that is present in that area, that is between the soil layers and the bedrock. Okay, so let's suppose this is your layer. Let's suppose this is the soil layer thickness, and it has the thickness h, and you have the velocity v, shear wave velocity vs, and under which you have half space. Okay, and as per the formula, the shear wave is equal to Vs upon 4h is equal to frequency, that is your fundamental frequency. The fundamental frequency is equal to shear wave velocity divided by 4h. Okay, so if you know this Vs value somehow, or if suppose you can just estimate, if you will take the average Vs value of top 30 meter of the soil, or maybe if you do not know the thickness of the soil or the layer, then you can assume some value, let's suppose 300 meter per second or whatever, and then if you know the fundamental frequency of from the HVSR curve, then you can easily estimate the thickness of the layer. Okay, that is the main idea of the HVSR curve. That is why the applications of the HVSR curve is to estimate the fundamental resonance frequency F0 of the ground, determine the depth to the bedrock and the sedimentary thickness. That is what we just did. We tried to find out the thickness of the soil layers, and after you find out the fundamental resonance frequency, and that is the frequency you generally want to avoid when you are constructing your structure or any kind of buildings in an area. So you do not want your resonance frequency to be matched with the fundamental frequency. So if you know this fundamental frequencies from this survey, then you can easily avoid that while doing any construction or design. So for seismic microzonation, that is why it is very useful, and it is also useful for site classification, because you can do the modeling of the HVSR curve. Using the inversion of the HVSR curve, you can find out the shear wave velocity, and using the range that we just saw, you can classify the site as A, B, C, D, and then this is further can be used for the civil engineering and the infrastructure planning. So now this figure that you see, this is the typical seismometer that we used in the field in order to compute the HVSR curve. So this was the instrument constructed or manufactured by a Italian based company, Micromed, and then they called it Tromino instrument. So you can couple it with the ground and record your continuous data for 30-40 minutes, and then it comes with a software named Gorilla, and using this software you can easily compute your dispersion curves. And there is some inversion schemes also present, using which you can fit your HVSR curve to calculate the shear wave velocity model. Okay, so you can see our aim is to find out the shear wave velocity model in order to characterize the soil underneath the subsurface. So this is the famous paper that was published by Nakamura in 1989. So a method for dynamic characteristics estimation of subsurface using microtremor on the ground surface. So they basically explained this paper. In this paper they put out the basic foundation of the HVSR technique, where they took certain assumptions and also showed using the well-log data how the various components can be imagined and taken into consideration in order to calculate the HVSR ratio, that is basically similar to the transfer function of the soil layers. Now what they have actually said, that before they basically put out the foundation, they emphasized upon to the why this HVSR technique is important, because you cannot do boring exploration. If you want to investigate a certain area, the boring exploration cannot be a solution, because in order to cover a wider area you will have to dig the bore holes at every place. Okay, so you must have to come up with some technique that may be indirect, non-invasive, non-destructive, in order to find out the site response of the area. So boring exploration will surely offer high accurate data concerning the dynamic properties of the subsurface. To understand the surface layer characteristics over a wide area, however, lots of boring must be made at high density. Boring exploration is therefore not a ready means, because it demands considerable manpower and substantial time and the tremendous cost, right? And if you look at the other ambient based techniques apart from HVSR, then they generally is being done at a very quiet time, at maybe the midnight, when the effect due to the particular source may be affecting your data. So they want to be done. Those techniques do want to record your data in the quiet time. But this techniques, basically HVSR technique, can be used almost at any time, even in the presence of certain coherent noises. So the surface layers are normally exposed to tremor by natural forces such as the storm and the sea waves, and artificial sources, plant, automobile, train, and etc. So sea waves induce a tremor of relatively long period, 2 to 3 seconds or more, and so that is called as microseism. So the tremor of relatively longer period, that means 2 to 3 seconds, is known as microseism, while the storm and the artificial sources or the forces do a tremor of short period, and that is known as microtremor. Okay, so shorter period noises are known as the microtremor. Now when any earthquake happens, so let's suppose this is the surface and this is your station, and there is an earthquake happening. So when you record your earthquake waves at a station, then what happens? So like whatever recording you are having, at the station, that is basically a function of source characteristics. It is also a function of the path it is following, and also it is having the near site effects or the effect of the instruments. Okay, so basically you are interested to find out what is the effect of the superficial layers. So this is what it is written: the earthquake happens due to the release of strain energy accumulated in the focal region along at the source location, and the part of the energy released from the surrounding. So dynamic characteristics are basically a function of radiation characteristics of the focal region, and also it is the dynamic characteristics of the wave motion propagation of the path up to the observation point, and also it is a function of the dynamic characteristics of the surface layers at the observation point. Now look at this diagram. They put this diagram in order to prove that why the superficial layers are only having much of the effect around the peak motion they are recording into their seismogram. So they have put in some of the earthquakes vertically here and associated seismograms. So these are the earthquakes here horizontally, and here you have the different locations where these earthquakes are recorded. Okay, so if you look at this earthquake, this is of magnitude around 2. Thereafter the magnitude is increasing from left to right. Okay, so if you look at this picture very carefully, what do you observe? So these seismograms are basically plotted for 5 seconds around their maximum value. Okay, so when you look at these seismogram, even though the earthquakes are different, these are different earthquakes, and these are recorded at a same location, such as this one, maybe Hiratuska. So this basically you can see from left to right, the pattern of the wave is almost same. Okay, pattern of the wave is almost same. Likewise, if you look at this one, this is almost same. It is looking somewhat same. Likewise, for other stations, the same thing has been observed. So even though the earthquake focus is different, the path is different, the most of the effect they observe is due to the superficial layers, right? That is why they are almost same. And you will also notice that the high frequency component or high frequency tremors are prevailing with the magnitude of a smaller size. Okay, so if you go from here to here, the periods are getting larger. Okay, so the high frequencies are basically observed in the smaller magnitude earthquakes. So now this is what they have concluded, that it may be said that the effect of the surface layers is most critical among the 3 factors in influencing the dynamic characteristics. That means you are having the effect of the superficial layers the most. Now they have done some observations to prove their points. So for example, they have conducted this experiment at a site known as Kamonomiya in Japan, and where they have recorded a continuous data for the north-south component for a period of 24 hours in 1986. So you can see they have started out the recording at around 6 p.m. and thereafter they have recorded this data up to 6 p.m. until the next day. And then what you will see, this particular earthquake or this particular data has been recorded in a very quiet time during the midnight, when the other artificial sources were almost shut off and there were no train were passing by. So this was a very quiet time. So you can see the largest micro tremor is observed during the noon time, and the smallest micro tremor is observed in between 2 or 3. Okay, this was the smallest. Okay, so if you look at the change between the velocity from smallest to the largest, that is around 0.5 to 3 meter per second multiplied by 10 to the power minus 5. And then you have the time change. So if you will plot this with respect to the frequency after doing the first Fourier transform, after taking the 1 hour windows, that means you are subdividing this entire continuous data into 1 hour each for 24 segments. Then you are taking the frequency on the y-axis and the amplitude on the y-axis. Then you will are plotting them together and overlapping with each other. Okay, so what will you observe? That the prevailing frequency that you see in each of the windows is around 1.5 hertz. Okay, now, so what they did after taking this observation, they have also compared it with the well-log data or the sonic data that they basically had it from their records for this particular region, that is for Commonomia. And here also they have observed that the prevailing frequency was around 1.5 seconds, 1.5 hertz. Okay, now they have also conducted other experiments like at Tabata and Ishibashi, and then at Tabata they used a 3-component seismometer, and the horizontal component being shown by the solid black lines and the vertical component is being shown by the dashed lines. Okay, here the ratio of maximum to minimum amplitude is more than 6, because this particular area was the area of intense social activities. So after they did the Fourier transform, after subdividing this entire continuous record into 24 hours, 1 hour each, then they have observed the prevailing frequencies are coming particularly in this particular region and also in this region. So that is because they are having this particular prevailing frequencies in this particular region, because that was the time when some train was passing by in that area when the data were recorded. So when they basically plotted the fluctuations of the prevailing frequencies of the microtremor with respect to the frequency for horizontal and the vertical component each, then they have seen the cluster of the prevailing frequencies at around in between 2 to 3 seconds and in between 5 to 8 seconds. Okay, these are the prevailing frequencies. So when they concluded their observations with respect to the Fourier spectrum of their amplitude, then they found that the higher amount of amplitude of the noise is occurring due to the presence of the train over there, and that might be affecting their data. But otherwise, the prevailing frequencies that is coming in between 2 to 3 seconds is mostly happening due to the geological structures present over there. Now, how did they come to the conclusion that the horizontal to vertical ratio is equivalent to the site response or maybe the transfer function of the region? So this is what they have said about their data. So it is said that the microtremor must be measured during the quiet time span. Indeed, the observation result at Commonomia shows that the tremor like specific vibration of the surface layers are strong during the quiet time span. However, at Tabata, it prevails during the quiet time span, appear to be related to the geological structures, which is considered for the engineering purposes. So a tremor with frequencies whose amplification, magnification increases as so-called estimated transfer function of the surface layers. It is generally said that the prevailing frequency of the microtremor fluctuates less, but prevailing frequency at Tabata and Commonomia fluctuated more depending upon the measuring time span. Okay, and such fluctuation may be due to the tremor source neighborhood of the measuring point. In other words, such tremor source may be considered as a noise of estimating the dynamic characteristics of the surface layer using microtremor. Okay, they have also concluded that the artificial tremor source has mostly the prevailing vertical motion and tend to induce the Rayleigh waves. So in case of Tabata, where the effect of the train induced tremor was remarkable in vertical component, that was maybe due to the Rayleigh wave that was induced by the train. Okay, now look at this particular diagram they plotted in this paper. So they basically plotted horizontal to vertical ratio for the earthquakes. Okay, the maximum peak of the horizontal to the vertical ratios. So what will you observe? Like at this, but they have recorded these earthquakes at these particular sites. So some of them are rocks, some of them are soft soils, and some of them are even extra soft soil. Okay, so if you look at the soft deposits like this one and this one and this one, apart from those, if they are recording it at the hard rock like this one and this one, so all are basically fluctuating nearby about 1. Okay, so that means what they were trying to prove is that the vertical and the horizontal motions, that means horizontal motion amplitude and the vertical motion amplitude are equal to 1 in case of hard rock. Okay, in case of hard rock it is equal to 1. So dividing the tremor into horizontal and vertical directions, it considered that the horizontal and the vertical tremors are similar to each other. For the hard rock, you can consider that the horizontal and the vertical motions are basically similar in all directions. Okay, so this is what they concluded. So, so horizontal tremor may be considered to a certain accuracy to be amplified due to the multiple reflections of the surface wave or the S wave, while the vertical tremor is through the multi-reflection of the P wave. So if you are considering the P wave velocity to be 1000 meter per second and the tremor is around 10 hertz or less, so you can say that the P wave reflections or the body wave contribution in the multiple reflection or the amplification is very, very less. So this is what it is written. The propagation velocity of the P wave is generally higher than 1000 meter per second, and the tremor of around 10 hertz or less may not be amplified so much through multi-reflection within the surface layers of the several tens meter at most of the thickness. So this is the basis they put out for finding out the transfer function. So as you know, transfer function is nothing but it is the ratio of the amplitude of wave in the surface layer to the amplitude in the basement layer, right? So so what you are doing, that at the surface whatever motion you are recording, you are dividing it by the motion recorded at the bedrock. When you take the ratio, that is your transfer function. So that is represented by ST. Okay, so this is what it is written, the spectrum ratio of the spectrum at the surface for the horizontal component. Okay, and this is the spectrum at the basement due to the horizontal component. So basically what they have done, they are considering that the effect of the Rayleigh wave on the vertical component is negligible. That means the vertical component spectrum at the surface divided by vertical component spectrum at the bedrock should be equal to 1. Okay, so they have actually shown it with the help of their realistic values using the well bore data. So you can see that this is fluctuating around 1. All these components are basically fluctuating around 1 only. So that is why the transfer function, that they call it ST, should be equal to the ratio of the horizontal component amplitude in the in the frequency domain to the vertical spectrum in the frequency domain, HYV. Okay, now so the same thing they have proved for taking the other data transfer function. So they have shown that here also that the transfer function is basically nothing but it is the ratio of horizontal to vertical spectrum. Now if we conclude that they have basically said that the method they have devised is for the dynamic characteristics and it can estimate the transfer function using the horizontal and the vertical components, that is basically the ratio of horizontal and the vertical spectra of the surface tremor, and it is an approximate transfer function. It is shown that the dynamic characteristic of the surface layers can be roughly understood at the seismic observation point if the three components we know. So you need a 3-component seismometer in order to have your HYV amplitude. So this is the criteria. If suppose you have computed your HYV amplitude or the curve, then you need to follow certain criteria that is basically floated by this project that we call it CSAME, that is the abbreviated form of site effect assessment using ambient excitations. And as per these guidelines, they have floated some criteria for estimating the reliable HYV curve, and there is a criteria for the clear peak in the HYV curve. Okay, so all these criteria need to be followed in order to have a greater accuracy of the HYV amplitude that you are observing. So we will not go into the details of these. Now we can also talk about the case study. Okay, so I have taken this paper that was written by one of my PhD student, Mr. Ravindra Kumar, in 2021. He did the site characterization and site response study of a region that is near to the Dhanbad region, like it is around 40 kilometers away towards Mathon Dam from here. And for this region, so this is the map of NIRSA. So you can see this is the entire area of Dhanbad and its adjacent regions, within which you have this NIRSA area. In this NIRSA area of around 5 by 5 kilometer, he has taken some of the observations using that Tromino instrument that I just showed you in the previous slide, and he almost taken 81 point data, and on each of the data he tried to compute the HYV curve. So these are some of the curves that he computed for the points that he took into consideration. So there were some points which were lying on the pond area or something, so he could not take the observations at those points. So you can see these are very nicely looking HYV curve. So this is the curve which is having this fundamental frequency here. The fundamental frequency for this point is somewhere here. So I told you like fundamental is frequency is associated with the frequency of the peak amplitude. Okay, now using the same points, all these points where the HYV curve was computed, he tried to model them. So in order to model them, he used a software known as Open HVSR, where they use the nonlinear optimization techniques in order to invert the HVSR curve to the shear wave velocity curve. Okay, so these are the shear wave velocities. So on the x-axis you see the shear wave velocities for different data points. So the data points is like NP01, NP02. So their names are basically, you can see in the map also. So these are the names. So like this is NP01 point, this is NP02. Likewise, there are several points they have basically taken. So some of the points data have been shown in the paper, and others were basically gone into the supplementary material. And then after doing the 1D modeling, so he basically developed the shear wave velocity model in 1D with respect to depth. Thereafter, we interpolated them in order to capture the 2D shear wave velocity image underneath the array of the observation points. So for example, if you look at this one, these points together, whatever model in 1D we got, we interpolated them, and then after interpolation, you got this particular image of the shear wave velocity. Okay, and if we interpolate their corresponding h by v curve or HVSR curve, then the image is looking something like this after converting them into the depth domain. Okay, so the similar fashion, the fundamental frequencies are following this particular pattern like this. Similarly, we also have the bedrock that is following the similar pattern into our 2D section. Similarly, we did it for other lines as well. So like for the second line, this one also we did the interpolation of our 1D model, and thereafter interpolation, whatever image we got, it looked something like this. So there was a data gap because the area, some part of that line was falling into the water area, so we could not took our data into that particular point. So that is why there is a data gap. And thereafter there were several other lines we consider. So these are the images that we got for the shear wave velocity variation in terms of 2D. And we also tried to interpret them, and after interpretation, whatever result we got, we published this paper into a peer-reviewed journal of natural hazards. Thereafter, HVSR. So far in the HVSR curve, what we learnt? So HVSR is a cost-effective technique that can be computed using a 3-component seismogram, and after we do the fast Fourier transform, we can basically divide the entire recording, continuous recording, into number of windows. For each window, we can do fast Fourier transform. Thereafter, we can take the mean of horizontal component and then divide it by vertical component. And this technique is very important for finding the fundamental resonance frequency of the soil present in the area, and also it is useful for finding the shear wave velocity of the soil under the area of the investigation, and also you can use it for doing the construction design, and also give these value to the civil engineer in order to have a better construction in the area. So next part of the lecture will go on to explain about the spectral analysis of surface wave. So that we will do it in the next class. Done. Any question? Okay.
Typing 20 is not determined the frequency of the structure, and it is that we know why showing of the structure in HVS terminal.
So using HVSR is not an active survey, okay? It is a passive survey. So whatever noise is coming from maybe traffic, human activities, or maybe the oceanic waves, that we are measuring, using which we can basically construct your HVSR curve. So far, I haven't seen doing anybody the active survey and computing the HVSR curve. So my answer is no.
It's good. So sanity gap needs to think like work on it.
Any research gap?
Is it?
There are many gaps. Okay, so like there is one gap that the HVSR curve that you are going to measure is predominantly having the body waves or the surface wave. That study you can do, okay, and come out with your results, okay. And also like for using the HVSR curve, like several areas are still looking forward to be getting investigated. So you can go and do your investigation. That is your one more research gap. So likewise, there are many that we can discuss after the class. You can take that into your project also.
One is this. So from frequency and activity cut off, we really determine the ESM definition is
Okay, that is a different section of this particular technique. So after you compute your HVSR curve, you are required to do the modeling. So in modeling, what you do, like you have your data and you want to convert their data using some inversion or modeling technique into the shear wave velocities. Okay. So for that purpose, like you are going to use some kind of optimization technique, either local optimization technique or the global optimization technique, where you are going to search for a model that can best explain your data or HVSR curve. Okay. So you will have to search your model space very rigorously in order to find that optimum model. Okay. So as I told you, you can do it either using like global or local optimization technique. If you have a good idea about your initial model, then local would be better. And if you do not have a good idea about your initial model, that may have some accuracy towards your realistic structure present over there, then you can go for global optimization. So that is a totally different geochemical inverse problem.